So in today's video, we're gonna start chapter number 12, which is a common carbonyl containing functional group. So in this chapter, we're gonna talk about some functional group that contain the carbonyl group, and we're gonna talk about what is carbonyl group. Then after that, we're gonna talk about some functional group which is aldehyde. Then we're gonna go on ketones, then carboxylic acid, then ester, and at the end we're going to talk about the amide, and then we're going to talk about what are those functional groups that we just talk about, aldehyde, ketone, and all the way to amide, and then what kind of chemical reaction they can perform and what are the physical properties because of the presence of these kind of functional group. So let's get started with today's lecture. So now let's get started with the introduction of the carbonyl containing functional group. But before we go into this topic, let's overview what are functional group that we already discussed on the previous chapter. So functional group is an atom or a group of atoms that combine to an organic compound to give that organic compound is specific physical and chemical properties, right? And we already talk about some of the functional group also on the last chapter that combine with an organic compound through a single bond. For example, we talk about an alcohol that has an OH group attached to an R carbon chain, right, through a single bond. Similarly, we talk about the thiol group where you have SH and then this SH group attached single bondedly with the carbon, right? So in this chapter, we're gonna talk about the functional group that has a special group present in there, which is a carbonyl group. So whatever the functional group that we're going to talk about in this chapter has this common feature present in all of the functional group, which is called as a carbonyl group. And if you can see over here, the carbonyl group consists of carbon and a double bonded to an oxygen atom. And because carbon has to make a 4 bond in an organic compound, so double bond is already attached to an oxygen, then the other 2 bond that we have on the carbonyl group, one of them can be an R group, which is a carbon chain. The other bond can be attached to a single atom or a group of atom, and then because of the attachment of different types of atoms or a group of atom, you will get a different types of functional group that we're going to talk about on the next slide, right? But in every functional group that we're going to talk about, this structure C double bond O is a common feature, so you will see in every functional group. So now let's talk about the geometry of this functional group, the C double bond O. So it has a planar geometry, and we know if any compound has a planar geometry, then you have a 120-degree bond angle between them. So the bond angle is 120, and we already talk about one of the bond out of the 4 bond can be an R group, which is a carbon chain or aromatic chain, you can say, or aromatic chain, and the other bond, the 4th bond, can be an atom or a group of atom that we already talk about. So before we go to the next slide, let's talk about the polarity of this functional group. So the time I see C double bond O and then O is more electronegative than carbon, means O atom is a stronger atom, and because of this you will get a partial negative charge on an oxygen and partial positive charge on a carbon. And because of the partial positive and negative, you will get 2 poles, and because of that the carbonyl group is a polar group because it contains a polar bond, right? So if you have 2 carbonyl group containing functional groups side by side, you can get dipole force of interaction because you have 2 pole plus and negative 2 poles, right? So this also be a common feature with all the functional group, that they can form a dipole interaction with each other, right? Okay, so now let's go to the next slide and then see what are those functional group that has this carbonyl group as a common group present in there. So if you see over here, we're gonna talk about the 5 common carbonyl containing functional group, and you have to remember all of them structurally, right? What's the difference between each of them? So let's talk about the first one. The first one we're gonna talk about is an aldehyde. So if you see, aldehyde has this common group which is a carbonyl group. Then we have ketone. Ketone also have this carbonyl group. Then we have a carboxylic acid, again same feature. Then we have an ester, same carbonyl group. Then we have an amide, same carbonyl group. So all the functional group has a common feature as a carbonyl group, right? We already talk about right now about all in each of the functional group that we have. Now let's see what's the difference between each of the functional group, right? Comparing with all other functional group that we have. So if we talk about the aldehyde, if you see that out of the 4 bond, 2 of them belongs to a carbonyl group on carbon. The third group is bonded with an R group, which is a carbon or any aromatic chain, and this is common also in all the functional group. If you can see over here, the only difference between all the functional group is the 4th bond. In aldehyde, the 4th bond has just hydrogen attached to it, and then because of the presence of just hydrogen on the 4th bond on that carbonyl group containing carbon, we call that functional group as an aldehyde. So aldehyde is a functional group that has C double bond O and then H. Let me draw it one more time. So sometime we write something like that, CHO. This is also your aldehyde, right? Because that carbon has a C double bond O and then the 4th bond is hydrogen. Let's talk about the ketone. If you see in the ketone, the 4th bond on the carbon is also again an R group, which is a carbon chain or an aromatic chain. So if you have on the carbonyl group, both side of the carbonyl group is attached to a R group, that means we have an ketone. Then we have a carboxylic acid. In carboxylic acid, what we have on the 4th bond, we have an alcohol. What's this OH group? This is your alcohol. So whenever you have a carbonyl group attached with an alcoholic group, we make a special functional group called as carboxylic acid. So don't get confused that it has the same property as an alcoholic group. So carboxylic acid group is a different than alcoholic group, because in carboxylic acid, in alcoholic group, you also have a carbonyl group, right? Then we have an ester. So in ester, the 4th bond attached have this functional group that has OR group, right? OR group. So this carbonyl group along with an OR group, we call that functional group as an ester. And R group we already know, right? This is a carbon or any aromatic chain, right? And for amide, what we have on the 4th bond, we have an nitrogen group or ammonia group, right? So you can have either hydrogen on both of the on the nitrogen, or both the nitrogen can be replaced by the R group, or one of the hydrogen can be replaced by R group and another one can be of hydrogen. So basically, if you have this kind of structure, C double bond O and then this carbon attached to the nitrogen, then we call as an amide group. And the bond on the nitrogen can be hydrogen, can be R group, right? It can varies. So make sure you know how to differentiate between all the functional group. If I say aldehyde, you should know this is a hydrogen. If I say ketone, the 4th bond attached to an R group. If I say carboxylic acid, then alcoholic group attached to a carbonyl group. And if I say ester, then OR group. Amide, the amine group, right? So this is how you remember it. So we're gonna talk about each of the functional groups separately and talk about their properties. So let's go to the next slide and then talk about all those things. So before we go to the specific functional group and talk about that thing, let's talk about briefly about the carbonyl group again one more time. so that we can cover every aspect of the carbonyl group. So we only talk about carbonyl group is a polar because of this bond. This will be positive, this will be negative, and because of creating a positive and partial negative, you create a pole, right? A dipole. So that's why carbonyl group always have a permanent dipole. So make sure this is also important. We already talked about on the previous slide. And because of the presence of the permanent dipole, all carbonyl containing group have dipole intermolecular interaction. So we already talked about also this thing on the previous slide. But some of the functional group that contain a carbonyl group can have a hydrogen bonding, and we're gonna talk about what are those functional group, right? For example, let's see the structure that is given on the top. So this is a carbonyl group, and then on carbonyl group what we have? A alcoholic group, and together carbonyl plus alcoholic, carboxylic acid group, right? So if you have a carboxylic acid functional group, it can form a hydrogen bond along with the dipole intermolecular force of attraction. Why? Because if you remember, any compound can form a hydrogen bond if that compound or that compound contain any of these hydrogen attached to any of the atom, right? Electronegative atom. For example, if you have oxygen, nitrogen, fluorine in an organic compound and that atom attached with a hydrogen, then these hydrogen can form a hydrogen bond with any of the three atom if you place nearby it, right? So if you see, the alcoholic group in a carboxylic acid has an hydrogen. If you see over here, this alcoholic group has an hydrogen that is attached with an oxygen, which is this condition. So carboxylic acid can form a hydrogen bond along with a dipole interaction because of the carbonyl group. So any organic compound that has a carboxylic acid present in there can form two type of interaction: dipole interaction and as well as a hydrogen bond interaction, right? Similarly, if you have any nitrogen hydrogen bond, where you can find in an amide, if you have this structure, a carbonyl group attached with an amine, right? So because of this, amide can form dipole interaction, and because of these bond, nitrogen and hydrogen, amide can also form an hydrogen bond. So it can also form two kind of interaction. So this is the way you can recognize which kind of interaction they can form. If you don't have any of these kind of bonding, nitrogen hydrogen, fluorine hydrogen, oxygen hydrogen in that particular functional group, that means that carbonyl containing functional group only can form a dipole intermolecular force, not a hydrogen bonding. So this is just a basic overview, so that when we go into the actual functional group, you should be able to understand why they are making a hydrogen bond and why some of them cannot make a hydrogen bond, right? So let's get to the next slide and talk about the actual functional group, right? So now let's get started with our first functional group that contain a carbonyl group, which is an aldehyde. So what are aldehyde? Aldehyde has a carbonyl group, and on the carbon, out of the 4 bond, 2 of them attached to an oxygen to make a carbonyl group, and then the other 2 bond, one of the bond is R group, the 4th bond has an hydrogen. This is the important thing. So in an aldehyde, carbonyl group attached to the 4th bond as a hydrogen, right? So let's take an example. There are some common aldehyde present. So this is a carbonyl group, then on the 4th bond you have hydrogen, but if you can see over here, the other bond also have a hydrogen instead of R, right? So if you can see this difference, so this is only an exception for the common aldehyde, which is only one carbon containing aldehyde. So we have a special name called formaldehyde or methanol. We're going to talk about why the name is methanol later on, but just remember this thing: the common aldehyde containing one carbon atom, just one, always has 2 hydrogen attached to the carbonyl group. But except that, if you have 2 carbon containing aldehyde, the other bond always have an R group, but in methanol or formaldehyde, the R group is replaced by the hydrogen. So just remember this thing. Let's talk about the other example. Let's see on this example. You have an R carbonyl group. What's this group? The R group. And then what's this group? This is an H. So you have an R, you have carbonyl, you have an hydrogen on the fourth bond. So that's why this is an aldehyde, right? And we already talk about, we can also show this structure C double bond OH in the form of CHO. If you see somewhere written as a CHO, that means we are talking about an aldehyde, right? And then we have an R, this R over here, right? So over here this is RCHO. And then we also learn about skeleton structure in the previous chapters too. So how gonna show that? So this is a loose structure that we are showing on the top. How are you gonna do the skeleton structure? How many carbon we have in here? We have 1, we have 2. So this is 2, 1, 2 skeleton line structure, right? And then if you remember that we just talk about in a skeleton line structure, you don't have to show carbon, you don't have to show hydrogen, but you have to show any heteroatom, means any atom beside carbon and hydrogen. So we have an oxygen in here, and that oxygen attached to the carbon through a double bond. That's why we have a double bond. So this is an skeleton line structure for ethanol. Similarly, if you have any aldehyde, this is your aldehyde, carbonyl plus 4, and then this is R group. How many carbon in this entire structure? 1, 2, 3 structure. So if I draw the skeleton line structure, we should draw the 3 carbon, 1, 2, 3, and then the first carbon attached to the oxygen through a double bond. And we are not showing a hydrogen over here, and we already explained, right? We already know about this thing, that we usually don't show hydrogen. So this is the way you normally show a skeleton line structure or a loose structure for an aldehyde molecule. So let's talk about aldehyde have a permanent dipole. We already know why, because aldehyde as a functional group containing a carbonyl group. What's kind of this group? This is carbonyl group. And then we already talk about in carbonyl group, oxygen is a negative and hydrogen is a, or carbon is a positive and partial positive, partial negative, right? And then because of the presence of 2 poles, positive and negative, we have a dipole. And if you remember, dipole always goes from positive end towards the negative end. That's why you're seeing that arrow, positive to negative, right? So if you have this dipole, so aldehyde can form a dipole intermolecular force of attraction because of the presence of dipole, right? And it's just not the case in aldehyde, in any function group that has a carbonyl group, right? We already talk about this thing. But it cannot form any hydrogen bond. Why aldehyde cannot form a hydrogen bond? If you remember, to make an hydrogen bond, this hydrogen has to attach, or any hydrogen has to attach with oxygen, fluorine, or nitrogen directly. But in this case, this hydrogen attached with the carbon, not with oxygen. So that's why this aldehyde cannot form a hydrogen bond, right? And because of this aldehyde is less soluble in water compared to the alcohol. If I compare alcohol and aldehyde, which one is more soluble in water? Why alcohol is more soluble in water? Why? Because alcohol has this functional group OH, and because of the hydrogen attached with an oxygen directly, this alcohol can make a hydrogen bond with water, but aldehyde cannot. That's why alcohol is more soluble in water. The second thing, alcohol can also form dipole interaction. Why? Oxygen is negative, hydrogen is positive in alcohol, same as carbonyl group and aldehyde. So the only thing that's making a difference is a hydrogen bond. So alcohol making an extra bond. That's why alcohol is more soluble in water compared to an aldehyde. But if I compare with any hydrocarbon, what are hydrocarbon? It can be alkene, alkane, alkyne, or aromatic compound. So if I compare with any alkane, let's say if you have 3 carbon alkane, what's this? Propane, right? And if I compare with the same 3 carbon containing aldehyde, 1 2 3, so aldehyde have a dipole interaction, or have a dipole, but alkane doesn't have any dipole because there is no dipole in there. So it has less attraction with water, because what is water? Water is a polar compound, and aldehyde has a polar group, right? Dipole. So dipole can interact with water, but alkane, which is a propane, one of the example, cannot form any kind of interaction with water except the dispersion forces which is present in every atom. So that's why aldehyde is more soluble in water compared to the hydrocarbons, because of the presence of a dipole, or a dipole interaction with water. So this is how you can comprehend that which kind of functional group or which kind of organic compound is soluble in water compared to the other one, depending on which kind of functional group is present in that organic compound. Right. Okay, so now let's go to the next slide and see how we can name an aldehyde. So now let's talk about the naming of the aldehyde. So there are 2 kind of naming. One of them is common name, that we normally use it, that for example, if an aldehyde contains just single carbon, for example, this is carbonyl group, this is the 4th bond, a hydrogen, but if it just has 1 carbon which is already in here, the other bond has to be only hydrogen. It cannot be an R group, right? That's why the name is formaldehyde. The structure is SCHO, or you can also write SCHO. Then if you have 2 carbon, then the name is acetaldehyde. For example, if you have this thing, CH3, C double bond O, H, then you have carbonyl group, then this is R group, this is H group. So this is an acetaldehyde with a 2 carbon, 1, 2. But we're gonna learn how to name an aldehyde using a scientific rule, or a IUPAC rule. So in IUPAC rule, we already talk about what are the rules when we talk about how to name an alcohol, thiol, alkane, alkene. You have to follow exactly the same rule. The only difference between all the previous rule and this rule is the ending word. Whenever you're naming an aldehyde, your ending word has to be end with AL, right? And then the second important thing is you have to give the preference to a carbonyl or to a functional group containing carbon. You have to start counting from that carbon that contain a functional group, right? So let's take some example over here. Let's try to name this structure. So the time I see a carbonyl group, time I see hydrogen attached to the carbonyl group, and the other group is an R group, I know this is an aldehyde group, and this organic compound is an aldehyde containing organic compound, right? So the rule says you have to give the preference. So let me tell you the rule again. You have to find the parent chain, you have to give the preference to the functional group. In this particular example was the functional group, aldehyde group, C double bond OH, and then this carbon, the carbonyl group, is a carbon that contain the functional group. So you have to give that lowest preference, or you have to start the counting from this side. So that's why it's 1, this is 2, this is 3. So if you have a 3 carbon containing compound, what's the name? Prop or propane. Let's write propane. But this is not an alkane, this is an aldehyde. So the ending word E will get replaced with Al. That's why the name is propanol. And you have to specify where you have an aldehyde group attached. If you remember from alcohol or a thiol, we have to give the location where the functional group attached on that parent chain, on which carbon. So in this particular case, the aldehyde group present on the first carbon, right? So either you can say 1 propanol, or you don't have to write 1. So if you don't write anything, we know this is on the first carbon. The first carbon is a carbonyl containing functional group, right? And if you need to draw this into a skeletal form, this is a skeleton form where we are showing the hydrogen, but or you can show like this, both of them are same, right? So this is how we name it. Let's try a couple of more example on the next slide. So let's try to name this organic compound with a functional group. First, your focus has to be which kind of functional group you have in that organic compound that is given. The time I see this C double bond O, I know this is a carbonyl group, right? We know this is carbonyl group. On one side, this entire structure is your R group, a carbon containing chain, right? All of them is carbon. So you got 3 bond, 2 bond with an oxygen, third bond is here. Where's the fourth bond? It's not showing over here. That means we are assuming the fourth bond is a hydrogen. That's why it's not shown over here. The time I know this is the fourth bond on this carbonyl group is a hydrogen, I know this is an aldehyde group. So we have to name according to an aldehyde. So let's apply the rule. You have to find the parent chain, the maximum carbon containing chain that you can go. And the rule says you cannot skip the carbon that has an aldehyde group or a carbonyl group. You have to include that functional group in your counting, right? And the third one, you have to give the preference to a carbon that contain the functional group, or in this case a carbonyl group, right? So we know this is a carbon, so we have to start from here. We cannot start from any other end, right? We already talk about this thing. So 1, 2, 3, I can go up, but I have just one more carbon, so that's why I'm not going up. 3, 4, I can go down. 5, 6, or I can go straight. 5, 6. It's up to you, because it doesn't matter which way or which direction we can count. Everything is going to end with only 6 carbon. So in this particular example, it goes straight 5, 6, but you could have gone down 5, 6. No problem in this particular example. So let's take the straight thing. So this is your parent chain, and everything that is not the part of the counting is your substituent. So this is your one substituent, one carbon is meth, and if you remember, the substituent name end with YL, so methyl. On the fourth carbon you have 2 carbon, and then 2 carbon is your ethane, but the ending word will be YL, ethyl. Right? So let's try to name it. So we have to just first find the substituent and then write the location of the substituent. And let's do, on the third carbon you have methyl group, on the fourth carbon you have ethyl group. So how you gonna name it? Even though ethyl comes on the fourth carbon, but whenever you write a name, you always write alphabetically. So ethyl, E comes first, then M, methyl. So that's why we have to write on the fourth carbon we have an ethyl group, then on the third carbon we have a methyl group. Then how many carbon in the parent chain? 6 carbon. 6 is your hexane, but you have an aldehyde group, that's why the ending word will be Al. So hexanal, right? So you can write 4 ethyl 3 methyl hexanal, or you can say 4 ethyl 3 methyl 1 hexanal. It's up to you, but we usually don't write 1, because if we don't write 1, we know this is on the first carbon, right? So this is how you name it. So let's try to do some more example on an aldehyde. If you have this structure, this is your chlorine, and then if you have this structure, So let's try to name these two, right? And then make sure you practice these kind of problem from your textbook too. So let's start with the first one. If you see, the time I see a carbonyl group, and if I don't see the fourth bond over here, because carbon has to have 4 bonds, but it has just 3, 2 with the oxygen, 1 with this R group over here. We don't have the fourth bond, so we are assuming the fourth bond is a hydrogen. That's why it's not shown over here. So this means this is an aldehyde group. We have to give the preference to the aldehyde group. So we have to start counting from this corner carbon. 1. Let's start 2, 3, 4, 5. Should I go up? No, because this is not a carbon. This is a chlorine atom attached to it. So we should go down, then 6. So how many total carbon in our parent chain, the longest chain? 6 carbon. And we have one substituent. This is chlorine. So if you have chlorine, how you write any heteroatom for any halogens? Chloro. If you would have bromine, F. Fluorine as a fluoro, so that's why you name it. So we should write 5 chloro. Then how many carbon in here? 6. 6 is your hexane, but this is an aldehyde, hexanal. 5 chlorohexanal. So this is how you name it. Let's try to name again the second one. Again, the time I see carbonyl group, C double bond O, we don't have the fourth bond. That's why this is a hydrogen. That's why we are not showing it. Again, an aldehyde. Right. So we have to give the preference to an carbonyl group in an aldehyde. Right. The carbon. So 1, 2, 3, 4, 5, 6. Right. Or you can go also up 5, 6. You can go this side 5, 6. So in each of the case doesn't matter, because you have one carbon extra in either direction, whatever direction you want to go. But I would take a straight if you have a choice. So always go a straight chain. So let's see, on the 5th carbon you have 2 branches, right? One branch is this, second branch is this. So this is one substituent, this is one substituent. So this is one carbon is methyl, one carbon is methyl. So how should we name this thing? So we should write 5. If you remember from the previous chapter, 5, 5, you have the same dimethyl, because on the 5th carbon you have one methyl group. Again on the 5th carbon you have second methyl group. So di means 2 methyl group. 5, 5, 5, 5 dimethyl, you have 6 carbon one more time. So hexanal. So this is the name. So this is how you name any aldehyde molecule. So make sure you practice from a textbook and try to name couple of them. So now let's go to the next slide, and let's talk about the solubility or the boiling point, right? The physical property of the aldehyde molecule on the next slide. So now let's try to do the problem based on the concept that we just learned about the hydrogen bond, dipole-dipole interaction, right? So let's rank the following compound from the lowest to the highest boiling point and explain your work. So the time I see the boiling point, so boiling point depend upon the kind of interaction that you have with each other, right? If they can form a hydrogen bond or a dipole-dipole interaction or a dispersion forces. So out of the 3 forces of attraction, which one is the strongest one? A hydrogen bond. So if any molecule that can form a hydrogen bond should have a higher boiling point compared to the one that cannot form a hydrogen bond. Same thing apply. If anyone has a dispersion or a dipole, then dipole will have a higher boiling point. Those compounds that can show a dipole-dipole interaction compared to only dispersion forces. So let's talk about all this kind in this problem. So we have 3 compounds, hexanal, 1 hexanol, heptane. So the time I see hexanal, ending word is al, I know this is an aldehyde. The time I see 1 hexanol, if you remember, oval represent alcohol. So this is an alcohol. And the time I say ane, this is simple alkane. a hydrocarbon, right? Alkane. So if you remember, in aldehyde is a polar molecule. Why? Because of the carbonyl group, and it has a dipole forces, right? Because aldehyde, if you remember, cannot form a hydrogen bond because hydrogen not attached with an oxygen. So let's make this structure hexagon. 1 2 3 4 5 6. This is your hexanol. Let's talk about the hexanol. So this is your hexanol. 1 2 3 4 5 6. This is OH, right? Carbon 1 2 3 4 5 6. This is 1 2 3 4 5 6, and this is heptane. Heptane is a 7. 1 2 3 4 5 6 7. So if you see clearly, only alcohol, it can form hydrogen bond as well as dipole interaction. Aldehyde can only form a dipole interaction, but for heptane only dispersion forces, because there is no dipole in this heptane. So if you see over here, the lowest one will be a heptane 1 because it has only dispersion forces. Then after that, aldehyde, which is an hexanol, only dipole interaction, whereas in B, which is an alcohol, it can form both hydrogen bonding as well as dipole interaction, and the time we see hydrogen bond, we know is the strongest kind of interaction. So you need more temperature to break that bond. So that's why it's a higher boiling point, right? So this is how you solve the problem, right? Depending on different functional group in a given organic compound. Now let's talk about the second functional group that contain a carbonyl group, which is a ketone. So if you see, what is ketone? Ketone is the same, containing a carbonyl group, but out of the 4 bond, two of the bond is with the oxygen, and the third bond is an R group, which is a common in all functional group. But the 4th bond, which is this bond, also is an R group, means carbon containing group. So when carbonyl group is become a sandwich between 2 R group, we call that functional group as a ketone, right? So let's take some example. If you see this structure, carbon R group, this is your R group, so R, C double bond O, R, ketone. Again R group, then C double bond O, ketone. So R group can be one side of the R group can be bigger compared to the another one, and vice versa, but the structure remain the same, R, C double bond O, R, right? So if you need to draw some skeleton line structure, if you draw this thing, this is 1 2 3, second carbon has a ketone. Again, this is R, this entire thing is R, C double bond O, R. Again, the third example, R, this is R group containing 2 carbon, this is C carbonyl group, right? R, C double bond O, R. So sometime you will see the condensed form written as, for this particular thing, as you will see something like this, R, C, O, R. So we should know this CO is a carbonyl group, something like this, right? So make sure you know the difference. What's the difference between ketone and the aldehyde? We just learned in aldehyde, this R group is replaced by a hydrogen in aldehyde, right? So this is how you normally differentiate. So one of the simplest type of ketone that you're gonna see in the laboratory, or you might have seen already, is acetone. So acetone is 2-propanone, right? So we're gonna talk about how you name an ketone later on, but acetone is a ketone that we normally use as a cleaning solvent, right? And you will see in the laboratory, whenever you're gonna work with, you're gonna see that acetone water bottle placed on the laboratory just for cleaning, right? So now let's talk about the naming of a ketone, how you name a ketone. So the rules remain the same like we use for alcohol, ketone, thiol, everything will remain the same. There is only two difference. One, the ending word will end with O-N-E, on or one, right? And the second rule is you always give the preference to a carbon containing carbonyl group in a ketone. You have to give the lowest number to that carbonyl group somehow, right? We're gonna do some example. So let's go to the next slide and we'll see some example how to name it. So let's try to name these two compound that we have over here. The name is already given, but we'll see why the name whatever is given. So the time I see this is R group, any carbon containing, this is also an R group containing 4 carbon, and what's this? This is your carbonyl group, right? So the structure is R C double bond O R. The time I see this structure, I know this compound contain a ketone, right? So now the question is, how you gonna number the ketone? How you going to name it? So we have a problem over here. In this ketone, if you see this carbon that contain a carbonyl group is not at the end of the organic compound. This is at somewhere in the center or somewhere in between the two carbon. And if we remember, we cannot start a counting or numbering of a carbon from any carbon which is in center or in between any two carbon. You always have to start a counting from the corner or terminal carbon. So we have two terminal carbon, this carbon and this carbon. So either I can start counting from here 1 2 3 4 or on this side 1 2 3 4. So we have to decide which one is the right way of counting. So according to the rule says you have to give the preference or the lowest number to a carbon containing a carbonyl group. So if I start from here 1 2, the second carbon contain the carbonyl group. If I would have started on the other ways, right, 1 2 3 4 5, the carbon that has a carbonyl group is occurring on the fifth carbon, but we already got on the second carbon, so we should start from this side, right? So that's why the numbering is 1 2 3 4 5 6. We have 6 carbon. 6 carbon is what? Hexane. But the time I say this is a ketone, so ending word will be O-N-E, 1. So instead of replace E with O-N-E, so that's why the name is hexanon, hexane on or 1. The time you see hexanon, we know this is a ketone, but you have to specify where you have the carbonyl group, because in ketone carbonyl group is not on the terminal, because if you don't write the number, we assume this is on the terminal carbon, and if you don't write anything, ketone cannot be present on the terminal carbon. So we have to specify the carbonyl group. So where you have a carbonyl group on the second carbon, so you have to spare 2 hexanon, right? So make sure you have to specify the carbonyl group in a ketone, right? The lowest number that you can get is 2, right? So sometime if you don't write the number, we know if you don't write it, we know that it's present on the second carbon, which is the lowest ketone can get, but still you have to write 2 hexanon or the number 2, the location of the carbonyl group, right? Let's talk about the second structure over here. Again, we have a 2 R group, 1 R group on this side, another R group on this side, then you have a carbonyl group, right? Now let's start counting again. We cannot start from this carbonyl group because this is in the center or somewhere between 2 carbon. We have to start from corners. This is one of the corner, this is second corner. So we started from here 1 2 3. The third one is getting a carbonyl group, but if we would have started from this side, then 1 2 3 4th, then fourth carbon have a carbonyl group, right? The carbon double bond, which is not possible because we already got the lowest number 3. So we have to start from this side. This is the right one, this is wrong. 1 2 3 4 5 6, again 6 hexanon, but you have to specify where you have the carbonyl group that makes the ketone. On the third carbon in a ketone, right? So 3-hexanon. Let's take one more example on the next slide. So let's try to name this structure over here one more time. So again, the time I see C double bond O, and we see you have R group carbon on the other two bond. I know this is a ketone. We have R C double bond O R. Right. Now we have to name it according to a ketone nomenclature. So what the rule says, whenever you count a parent chain, you have to give to the lowest number to a carbon that has a carbonyl group, right? And you have to include that carbonyl group in your counting always. So we can start from this side, or we can start from this side, we can start from this side, the corner terminal carbons. Let's start from this side. 1 2 3 4 5. Then on after 5 I can go down 6 or 7, or we can go straight 6 or 7. So in this case we go straight, because if you have a choice, you should always go with the straight chain, right? So we are going for a straight. Then that means this is our parent chain, the maximum number that I include. And on the third carbon we have a ketone, the carbonyl group, right? But we have some substituent also. You have 1 carbon methyl, you have 2 carbon ethyl. So we have to name it alphabetically. E comes first, then M. So we should write the location on the 5th carbon. You have ethyl group. On the 2nd carbon you have methyl group. And how many carbon in your parent chain? 7 carbon. 7 is heptane, but this is a ketone, heptanon, right? And the one last thing that you need to write, don't forget, you have to tell where do you have the carbonyl group for that particular ketone, is on the 3rd carbon. If you don't specify, that means the structure is wrong, you name it wrong. So on the 3rd carbon you have a ketone group, right, or carbonyl group. So this is how you name it, right? So make sure you practice from a textbook, couple of more example, apply the same rule that we just learned, and try to name it, right? So let's try to do some more example on a ketone. So till now we just did the aliphatic carbon that has a ketone, but what about if the organic compound is a cyclic compound? So what is cyclic? If you have something like this is a 4 carbon, right, cyclic, what should be the name? If you remember from a hydrocarbon, this name is cyclobutane. You have 4 carbon in a cyclic compound, right? But if I modified this compound with something like this, then what's this compound then right now? This is a ketone. How would I know this is a ketone? Because this carbon, which is a carbonyl group, attached with the carbon, this carbon also attached with the carbon, so that means R C double bond O R, right? RCOR, ketone. So how you normally name it? So the naming should be the same. This is a cyclic compound, you should write cyclo. How many carbon? 4 carbon. 4 carbon is butane, but because this is a ketone, cyclobutanon, right? So this is the naming. Should I write something 1 cyclobutanon? No, because if you remember, if you want to write, you can write, but in a cyclic compound every carbon is similar, right? So if you don't write it, then we are assuming then the ketone group is present on the 1st carbon over here. So that's the difference. In a cyclic compound you can give a carbon as number 1, but where is an aliphatic carbon, the carbonyl group cannot be present on the 1st carbon. That's the difference between cyclic compound containing ketone compared to an aliphatic, right, without a non-cyclic compound, right, where you have the carbonyl group, the lowest you can get is 2. Let's try to name couple of more. if you have this compound, the time you see this compound, this is a carbonyl group, this is carbon, this is carbon, right? So R C O R, right? This is a ketone. So we got this is a ketone, but how you name it? And we have two substituent. This is a substituent, right? So we have to give the preference to a carbonyl containing carbon. So in this case, this is 1. Then you have to give the lowest preference to the substituent. If I go over here, 1 2 3 4 5 6, so the substituent is getting third and fourth. But if I would have gone the other way around, 1 2 3 4 5 6, then the substituent will get 4 and 5. So this is the wrong case. Then we should go anti-clockwise, 1 2 3. Then what should be the name? Name will be 3 4 dichloro. Then you have 6 carbon, but this is a cyclic compound, so you have to write cyclo. 6 carbon is hexane, but this is a ketone, ONE, cyclohexanone. Right? And we usually don't write 1, because if you don't write 1, we know this is on the first carbon. So that's why in this particular case, in cyclic compound, we are not writing 1 2 3 for hexanone, right? Because if any ketone is present, you should or will always give out number 1 to that carbonyl group, right? So that's the difference. So make sure you also know how to write a ketone in a cyclic form if the carbon group is present, right? Okay, so let's try to do this problem over here. The problem says the open chain form of desorbose, one of the sugar molecule, a simple sugar, is given below. Highlight and label all the functional group that we have. So let's see how many types of functional group that we have. The time I see OH, this is an alcohol, this is alcohol, this is alcohol, alcohol, OH, alcohol. But the time I see this thing, this is a carbonyl group. So we have two types of groups, alcoholic group and carbonyl group. Okay, let's do one more problem. So till now we just learned how to name the ketone if the structure is given. But what if the name is given, how you going to draw the structure? So we're going to learn about those things on this slide. So let's take an example. If we are given with the naming, how we going to draw the structure, right? So let's do it. So I would suggest always go from the back side over here, right, from the parent chain. So the time I see octane, I know this contains 8 carbon. And what is ONE? The time I see ONE, I know this is a ketone. And where we have a ketone? On the third carbon. So let's draw it. 1 2 3 4 5 6 7 8. We already drew 8 carbon, right? And on the third carbon you have a ketone. So we're done with this thing, entire thing, right? Now on the second carbon of our parent chain, you have a methyl group. So this is our second carbon. This is your substituent then, right? So this is how you normally draw a structure if the name is given. So we just done with ketone, but you can use the same concept for any kind of functional group if you have to draw the entire structure. Let's do one more time over here. So you have to go from the parent chain, octane, again 8 carbon. Let's draw 8 carbon. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. And then the time I see ONE on, I know is a ketone. On the second carbon of you have a carbonyl group, right? So this is your ketone on the second carbon. And on the third carbon you have a methyl group. So this is methyl group as a substituent, right? So this is the structure. So make sure you also practice how to draw a structure from the naming, And then if you know how to draw these two structures, you can apply the same kind of concept to draw any structure containing any functional group. Right. Now let's talk about the another types of functional group that contain a carbonyl group, which is a carboxylic acid. And we already talked about what is carboxylic acid. This is RC double bond O OH. So you have a carbonyl group, attach the fourth bond, one of the bond attached with the R group, right, which is a common, but the fourth bond in this case is not hydrogen, it's not R group, is an alcoholic group. So whenever a carbonyl group attached with an alcoholic group, that entire thing become a carboxylic acid. So this is your carboxylic acid group, right? Carbonyl plus hydroxyl group, the OH group, right? And where you can find this carboxylic acid, mainly in many metabolic intermediate in a cell. There's a certain intermediate that the cell normally make during a digestion or during metabolic reaction. Some of the intermediate can be of carboxylic acid containing compound. And the time I see this is an acid, so carboxylic acids are weak acid and their property depend on the pH of the environment, right? And how you normally draw or write the carboxylic acid, sometimes we draw the entire structure like this, sometimes we just write RCOOH, right? Because what is RCOOH? This is R, this is C, this is OOH. And sometimes you will see in the textbook this is also can be written as RCO2H because you have two oxygen, that's why I'm writing O2H, right? So there are different way of representation of this carboxylic acid. So if you see there are a couple of examples, let's talk about the carboxylic acid. The simplest carboxylic acid, you have this group C double bond O with an OH group, carboxylic acid. So the simplest carboxylic acid doesn't have any R group, it has hydrogen. That's the only simplest carboxylic acid, the single carbon containing. How many carbon you have in there? One. So the common name is formic acid. And we're gonna talk about why the name is methanoic acid, right? Except the methanoic or formic acid, every other carboxylic acid has the same structure, R, C double bond O, OH, right? Then we have R group again. In this, the third example, what is this R group? Benzene, right? And then you have this carboxylic acid group, right? So we're gonna talk about later on why the name is this, but just focus right now about the line angle formula or skeleton line structure, right? So this is a skeleton line structure, C double bond OH, because we have to show, if you remember from the previous chapter, you have to show that any heteroatom as well as the hydrogen attached with the heteroatom. That's why there is a hydrogen you can see over here in OH. So this is how you can represent. So now let's try to see how you can differentiate between alcohol and carboxylic acid. So carboxylic acid, you have a carbonyl group and a carbon that has a carbonyl group attached with an oxygen or attached with a hydroxyl group, the OH group. This entire thing is your carboxylic acid. But if you see a carbon attached with an hydroxyl group and that carbon doesn't have any carbonyl group, so that means this is an alcoholic group. This is not a carboxylic acid group. Again, carbon attached with an OH and that carbon doesn't have any carbonyl group, that means that is an alcohol. So remember this thing. You always ask yourself whether the carbon has a carbonyl group that has an OH group attached to it. Let's do one problem on this. What's the difference between an alcohol, phenol, and a carboxylic acid? How you can differentiate between them? In alcohol, You have OH group, hydroxyl group attached with the carbon that doesn't have any carbonyl group, right? In phenol, you have a benzene, you have OH, then the carbon of the benzene attached with an OH group, but it doesn't attach with the carbonyl group, right? The double bond of oxygen. This is phenol. But for carboxylic acid, the carbon that has an OH group, alcoholic group, also attached with the carbon double bond O, also contain a carbonyl group. So this is your carboxylic acid group. So this is how you can differentiate, right? So now let's talk about the carboxylic acid and carboxylate ion, right? What does it mean? So carboxylic acid, we already talk about, is a weak acid, and we know the definition of an acid. What are acid? Acid are those compounds that can donate a proton in a solution, right? Or during acid-base reaction, acid are those compounds that can donate a hydrogen, right? Or lose a hydrogen. So let's take this example over here. This is a carboxylic acid, and this is the hydrogen in this carboxylic acid, which is acidic, right? React with water. Water in this case is acting as a base. Why? Because carboxylic acid is going to donate a hydrogen to this oxygen, and by itself convert it into a ion, right? And then the water is going to get that proton and convert it into ion called hydronium ion. And the structure we have for carboxylic acid, after we done donating with the hydrogen, we call as carboxylate ion, and this is a conjugate base of an acid part, and the water which act as a base is now as a conjugate acid. Right? So the carboxylate ion, this, if you see, this is a weak acid, that's why we have an equilibrium double-sided and arrow, right? The reaction will go in either direction depending on the physiological pH, the pH of the solution, and at physiological pH, which is 7.3 to 7.535, the reaction is favored the carboxylate ion. So you will see mostly carboxylic acid in a cell. If any reaction is going on, you will always see a carboxylic acid in the form of a carboxylate ion, because the physiological pH is 7.3 in a cell. So don't get confused if you're saying carboxylate ion instead of a carboxylic acid, the entire structure, right? So from now on, if you see something like this structure, this is a carboxylate ion, right? Comes from the carboxylic acid. Now let's talk about the physical properties of the carboxylic acid or a carboxylate ion. So in carboxylic acid, if you see this structure, you have two carboxylic acid in here, 1, 2, right? 2 carboxylic acid, and if you can see, both of the carboxylic acid molecule can form two hydrogen bond within each other. So one of the hydrogen bond comes from the carbonyl group of the carboxylic acid, and a hydrogen comes from the alcoholic part of the carboxylic acid, right? This is a hydrogen bond. Again, the second molecule also have a carbonyl group, and the other molecule also have a hydrogen attached with the alcoholic part, so it can also form a hydrogen. So remember this thing, a carboxylic acid can form a dimer, means two molecules can form two hydrogen bonds, and because of the formation of two hydrogen bond within the two molecules, it has the highest boiling point, because none of the other functional group can make two hydrogen bond when they interact with each other within the same molecule, right? Carbox, alcohol and alcohol. Let's talk about the alcohol. OH, if you have one more alcohol, ROH, how many hydrogen bond it can form within the molecule? Just one, right? Then you will have one right? So remember this thing. If you have to compare the boiling point of carboxylic acid and an alcohol, carboxylic acid has a higher boiling point compared to an alcohol, right? Because it can form a dimer. Now let's talk about the hydrogen bonding and the physical property of the carboxylic acid and carboxylate ion, right? Again, how you can differentiate between the physical property of both of them. So we know carboxylic acid is a neutral molecule, right? Because carboxylic acid is RC double bond O OH, whereas a carboxylate ion, which is R double bond O negative, because hydrogen is already been donated to a base, is a negatively charged molecule, and because of the presence of the negative charge, carboxylate ion can form ion dipole interaction with water molecule and making them more soluble than their acid counterpart, which doesn't have any charge on it, right? And can only form a hydrogen bond. So ionic compounds are more soluble compared to the compound that can form hydrogen bond, right? Then the solubility of the carboxylic acid, if you talk about just the carboxylic acid, it depends on how many carbon atom you have it. For example, let's say if you have 1 2 3, then this is your carboxylic acid, C double bond OH. If you have how many carbon in there? 1 2 3 4. So this can be a soluble, but if you increase the number of carbon, then only one carboxylic acid functional group cannot solubilize all the part of the carbon, because carbon are hydrophobic or non-polar. So one functional group cannot able to solubilize all the carbon atom, right? So there is a limit of carbon atom, the ratio. So the ratio can be 4:1 or 3:1. So one functional group of carboxylic acid can solubilize only a compound that contains 3 carbon, right? For example, if you have just this is your carboxylic acid, C double bond OH. How many carbon it has? 1 2 3. So this single carboxylic acid group can solubilize all 3 carbon. But if you increase the length, then you are making the molecule non-polar, because one cannot solubilize all the carbons in there. So make sure you know this relationship too. But if you put some more carboxylic acid in there anywhere, right? If you put 5 carboxylic acid in this big number of carbon containing compound, then it might be soluble, because the ratio is getting increase of the carboxylic acid group. So this is just the ratio, right? So make sure you remember this concept too. So let's try to do this problem over here. The structure is given on the right hand side, and you have what you need to do. You have to circle and identify the phenol if there is any ether amine carboxylic acid functional group, and is the carboxylic acid in its neutral form or ionic form, right? Or is the amine in its neutral form and ionic form? So you have to answer all these things. So let's say, where is your phenol? So benzene plus OH, that's your phenol, right? That's your phenol. Then you have C, this is a carbon, comes from the benzene. This is another carbon from second benzene, and you have COC, this is your ether, right? Then we have amine. What is amine? Amine is RNS2. If you remember, single bonded nitrogen attached with the carbon. So this is your carbon attached with the nitrogen, that's your amine. Where is your carboxylic acid? Is this one, carbonyl group, this carbon attached with an oxygen, and you have a negative charge. So this is a carboxylate ion, not a carboxylic acid, because the acid part is already been donated, right? So you can say the carboxylic acid part is in ionic form, right? Carboxylic ion, and the amine form is a neutral form in this case, because you don't have any charge on the nitrogen, right? So this is how you can differentiate different functional group in a organic compound or any structure. Now let's learn how to name an carboxylic acid using a IUPAC rule, right? So rule will be the same, right? I'm not gonna go again with the same rule. The only two differences, you have to give the preference to a carboxylic acid functional group, and you have to include the functional group in your counting whenever you do a parent chain counting, right? So let's try to do the name. And the third one, the ending word will be oic acid. Like for aldehyde we have Al, for alcohol we have Ol, right? Similarly for carboxylic acid the ending word is oic acid. So let's try to name couple of them and try to learn. So the time I see this C double bond O and the same carbon has an OH group attached, I know this is a carboxylic acid group, right? And we have to give the preference to a carbon that has a carboxylic acid. So if you see clearly, the carbon is already a part of the carboxylic acid group, so we can start from this carbon as number 1, right? This is a terminal carbon, right? So make sure you have to include a carbon in a carboxylic acid, a carbon in a ketone, a carbon in an aldehyde, because everything in every functional group, carbonyl group has a carbon, right? So 1, 2, 3, 4. If you have 4 carbon is butane, but this is a carboxylic acid functional group present in butane, so we remove E, and instead of butane we are putting oic acid, so butanoic acid, right? And then where's the carboxylic acid group? 1, so you can write 1 butanoic acid, or usually don't write 1, because if you don't write it, we know the carboxylic acid is present on the first carbon. Same thing in a line structure formula, 1, 2, 3, 4 butanoic acid, right? What's the name of this structure over here? So if you count, this is a carbonyl group, C double bond O, and the carbon that has a carbonyl group again attached with an OH, so I know this is a carboxylic acid. So we have to include a carbon as number 1 on a carbonyl group, 1, 2, 3, 4, 5, 6. So 6 is your hexane, but this is a carboxylic acid, hexanoic acid, and either you can write 1, and if you don't want to write 1, is also hexanoic acid. So this is how you name it. So let's try to do the naming for this compound. The time I see C double bond O, OH, carboxylic acid, then you have to give the number 1 to the carbon that in the carboxylic acid. So 1, 2, 3, either you can go up, this can be 4, or you can go this side, this can be 4, or you can go this side, this can be 4. So it's up to you, because it doesn't matter which direction we go, we have just 1 extra carbon, but you always go a straight one, so we are not using this as 4. So if we are not using, then this can act as a substituent, so you have 1 carbon, 1 carbon, so both of them are methyl substituent. This is your parent chain, right? So we have to write on the third carbon we have 2 substituent, 3, 3, because both of them are same, methyl methyl, dimethyl. How many carbon in your parent chain? 1, 2, 3, 4. 4 is butane, because this is a carboxylic acid, butanoic acid. So 3, 3 dimethyl butanoic acid. So this is how you normally name it. So now let's try to name couple of the carboxylic acid, the IUPAC name. Let's start with the first one. The time I see this thing, this is a carboxylic acid, and we have to start with the carbon of the carboxylic acid. 1, 2, 3, 4, 5. 5 is pentane, ending word is oic acid, pentanoic acid. Let's do the fifth, B1, again carboxylic acid functional group. We have to include a carbon of the carboxylic acid. 1, 2, 3, 4. 4 is butane, butanoic acid. let's do this one. The time I see C double bond OH, carboxylic acid, 1 2 3 4 5 6 7 8 9. 9 is non-anoic acid. Let's do the D part. So the time I see this carboxylic acid, we have to include this as a number 1 2. I can go down, but I can say there's more structure of carbon. Then we can go 3 4 5, or I can go up or down. Let's go straight 6, because it doesn't matter, because we will end up with 6 carbon. Then that means this is our substituent, 1 carbon. 1 carbon is methyl. Second substituent on the 4th carbon, methyl. And then the third substituent again methyl. So I can name 2, 3, 4, because on the 2nd carbon, on the 4th carbon, and on the 5th carbon we have methyl group, and we have 3 of them trimethyl. How many carbon in the parent chain? 6, hexanoic acid. So 2 3 4 trimethyl hexanoic acid. So let's do some more example on the carboxylic acid. If we have what's the name of this? So if you have, what's the name of this one over here? This is a benzene. So if you have, and what's this? This is a carboxylic acid, Ca. So if a carboxylic acid is present on the benzene, we have a name called benzoic acid, right? So if we know benzoic acid, so if I draw this structure, benzene, and you have COOH, and if you remember, the time I write COOH is also a carboxylic acid, right? If I draw Cl and Cl, what's the name? Then we have to give the number 1 that has a carboxylic acid, right? Then 2 3 4 5 6. So we can say 2, 4 dichloro. And what is benzene plus carboxylic acid? Benzoic acid. That can be our parent chain, benzoic acid. 2,4 dichlorobenzoic acid, right? So this is one way of writing the name of any compound that contain benzene and a carboxylic acid. So let's do one more example on the carboxylic acid naming, but this time we're gonna give you the name and you're gonna draw the structure, or we're gonna learn how to draw the structure if the name is given. So if the name is 2, 4 dichloro-pentanoic acid, what should be the structure? And that second name is 3-ethyl benzoic acid. Then what's the structure? So let's do one by one. So like I said, if you already done with the ketone, you have to apply the same concept, how to draw the structure. Always go from the parent name. What's the parent name? Pentanoic acid. The time I see pentane and oic acid, I know you have a 5 carbon and you have a carboxylic acid. So let's do 1 2 3 4 5, and you have carboxylic acid in there, right? So this C double bond O and OH, this is your carboxylic acid, right? Then on the 2nd carbon and on the 4th carbon of this pentanoic acid, you have 2 chlorine atom. So we have to give 1 to this carbon that has carbonyl group, 2 3 4 5, and on the 2nd carbon you have a chlorine, so I'm going to put chlorine, and on the 4th carbon you have a chlorine one more time. So this is a structure of 2, 4 dichloropentanoic acid. Let's do the second one, 3-ethyl benzoic. First you write the parent name, which is benzenoic acid. So I know what is benzoic acid. So benzoic or benzenoic acid, same thing, benzene plus carboxylic acid. So benzene, and you have a carboxylic acid, COOH, right? And on the third carbon you have an ethyl group. So this is your first carbon. You have to give the preference to a carbon that has a carbonyl 2, 3. On the third carbon you have ethyl group. So this is your 3-ethyl benzoic acid. Make sure whenever we say benzoic acid, we are not including this in accounting. So this is the difference. Make sure you remember this thing. You cannot count from here 1, 2, 3, 4, 5. This is wrong. You have to include a carbon from a benzene that has a carboxylic acid attached to it. So that's the difference between a common carboxylic acid where you have a carbon that has a carboxylic acid you have to count, but in benzoic you don't have to count this carbon. So that's the difference. So make sure you know this small differences. So now we're going to talk about another functional group, which is an ester. So ester is prepared by a carboxylic acid. So that's why we normally call ester as a derivative of a carboxylic acid. So what is an ester? RCOO. This is your carboxylic acid, right? How you gonna make an ester? So you remove a hydrogen from a carboxylic acid and replace with an R. So whenever you have OR group attached with a carbonyl group, which is we call as an ester. And what's the difference between carboxylic and an ester? It's just a difference of H and R. If you put an H, then it becomes carboxylic acid. If you remove H and replace with an R, any carbon containing compound, then it becomes an ester. So ester is RC double bond OR. This is your ester group. So make sure you know the difference, right? Like this. You have C double bond O, then OR, an ester. And many esters are normally gives a fragrant smell or pleasant smelling smell. So this is how you can also determine if you're doing any work in the laboratory, then you can differentiate a compound from an ester by its smell, a pleasant smell. So let's take a couple of examples over here. You see this is R, this is C double bond O, this is OR, right? So this is an ester. Again R, C double bond O, OR. This is an ester. So ester is this, R, C double bond O, OR, right? Together it's an ester. So in the line angle formula, the skeletal line, you can see C double bond O, then OR. This is an ester group. So once you can identify an ester group easily, you can name the ester or you can do any chemical reaction with an ester, right? So but first, the most important thing, can you identify the functional group in a given organic compound, whether it's in carboxylic acid, ester, amide, alcohol? That's the only requirement right now, right? So one of the things students normally get confused between is ester and ether. So ester are not ether. So what are ester? Ester is R, C double bond O, R. And what is an ether? R, O, R. So what's the difference between ester and ether is you don't have a carbonyl group in there between R, O, R, right? So make sure you know how to differentiate ether and ester. So this is an ether, COC, but this is an, can you say this is an ether, R, C double bond O, R? So this COC, because R is what, carbon containing compound, this can be C again. So this is not an ether because this is not a simple carbon, this is a carbonyl group. So if you have a carbon group and then OR, that's an ester. But if you have something like this COC and you don't have any carbon group on any of the carbon, that's an ether. Right? So make sure you know how to differentiate. So now let's talk about the physical property of an ester. Ester has a permanent dipole. Why? Because it has an carbonyl group and form dipole-dipole interaction. So any functional group that has a carbonyl group can form a dipole-dipole. We already know about this thing. But there is no OH or NH group or bond present in the ester. Is there any hydrogen attached with an oxygen? No. So ester cannot form a hydrogen bond. So that's the important thing, right? So if you have many carbon atoms, then mostly nonpolar and hydrophobic. If this R group is too big, for example, if you have something like that, C double bond OO, and this R can have multiple carbon, then ester is non-polar and hydrophobic because dipole-dipole force of interaction cannot help to solubilize all the high number of carbon that is attached to this functional group, right? And it has higher boiling point than similar alkane. If you compare with an alkane, it has a higher boiling point because alkane doesn't form any dipole-dipole interaction. So this is a benefit for, or ester has an upper hand or an ether, but it has a lower boiling point compared to alcohol and carboxylic acid. Why? Because an alcohol and carboxylic acid can form dipole-dipole interaction as well as the hydrogen bonding. So this is how you normally decide the boiling point, right? So alkane have the lowest boiling point and carboxylic acid has the highest boiling point if you compare the same number of carbon, right? Let's go to the next slide and then try to understand this concept again. If you see, we have alkane, ether, ester, alcohol and carboxylic acid, and then we are comparing the boiling point, right? So any alkane has the lowest boiling point because it has just dispersion forces in there, which is the weakest kind of force of attraction. Ether has a dipole-dipole because this is partial negative positive, this is partial negative, this is partial positive, right? So it is a weak dipole-dipole, but ester has a strong dipole-dipole force of attraction, right? Because this is positive, this is negative, this is can be negative, this is carbon positive, strong dipole-dipole. So that's why it has higher boiling point compared to the ether. But alcohol has higher boiling point than ester because it can form hydrogen bonding, presence of this OH bond. And carboxylic acid has the highest boiling point because it can form 2 hydrogen bond within the molecule. So we already talk about, when we talk about the carboxylic acid, it can form a dimer, right? So yeah, so if I ask you arrange all these functional group according to their boiling point, make sure you know how to differentiate, how to arrange this thing from lower to higher, higher to lower, right? So let's do one problem. Rank the following compound from most soluble to a least soluble. So out of the 3 compound that is given, what do you think, which one is the most soluble? So if you see over here, this is which kind. The first thing that you need to know is which kind of functional group that you have. Over here we have a carboxylic acid, this is just plain alkane, a hydrocarbon, and this is C double bond OR, this is an ester, right? So carboxylic acid is the most soluble because it can form a hydrogen bond with water, right? Then we have an ester because it has dipole-dipole interaction. Water is a dipolar or has a dipole, so it can interact with water. Then we have A. But alkane doesn't have any dipole or hydrogen bond that it can form with water, but it can just form dispersion forces, which is the weakest. It's not strong, so it's not soluble, right? So the sequence will be most soluble C, then A, then the last is B. So if you know the functional group, if you know which kind of interaction they can make, if there is any hydrogen bond, dipole, no dipole, then you can easily differentiate. So that's why the concept is very important. So make sure you know the concept. This will help you in the long run. Now we're gonna know how to name an ester, right? The IUPAC name for an ester. So the first thing you have to see in a structure of an ester, you have two R group, 1, 2. So the R group that is attached with a single oxygen, right? We treat this as a substituent. So remember this thing, the R group that attached directly with the oxygen. The other R group that is attached with the carbonyl group, we treat this as a parent chain. And then once we know the parent chain, we know the substituent, we know how to name it. And the ending word of any compound that contain an ester should end with OATE. OAT. Like for alcohol, we have OL, aldehyde AL, carboxylic acid, OIC acid. Similarly for an ester, ending word will be OAT. So let's try to name a couple of examples on the next slide, right, based on the thing. And again, you have to just follow all the rules, right? Let's do on the next slide. So let's try to name this compound that we have. First, the foremost thing that you need to ask yourself, which kind of functional group is present, if there is any. So the time I see C double bond O, and this R, so this is R, C double bond O, R. This is an ester, right? So the R group that is present with an oxygen, we treat this an alkyl group. So how many carbon in here? We have 2. 1, 2. 2 is your ethane, ethyl. That's why we have a substituent as ethyl. What's your parent chain? 1, because we have to include the carbon. Make sure you always include 1, 2, 3, 4, 5, 6, 7, 8, 7. Then 7 is heptane, but the ending word is not ane, is O8. So heptanoate, heptane O8, the ending word. So ethyl heptanoate. So this is how you normally name an ester. Right? Let's do some more example on the next slide and try to learn something more, right? Practice more. So let's try to name couple of an ester, the IUPAC name. Let's do the first one. The time you see C double bond O R, C double bond O R. So this R group that attached with an oxygen is a substituent. So how many carbon in there? 1. 1 is your methyl. So methyl as your substituent. And how many carbon in the parent chain? 1, 2, 3, 4. 4 is butane, butanoate. The ending word will be OATE. Butane means 4 carbon. Let's do the B part. The time you see C double bond O, right, this is R group, this is R group, ROOR. So this R group is a substituent because it attached with the single oxygen. So 1, 2. 2 is your ethyl, so that's why the substituent is ethyl. How many carbon in the parent chain? 1, 2, 3, 4, 5, 6, 7. 7 is heptane, and the ending word is O8, heptanoate, right? Let's do the third one, which is as CO2CH3. I can draw the structure H. CO2 means you have double bond on carbon, then you have one more oxygen, then CH2, CH3. And if you see it clearly, this is an ester, right? And then instead of R you have what? Hydrogen. So this is a simple ester, right? Just one carbon containing ester. So this oxygen attached with this carbon, single oxygen. So this is as a substituent 1, 2. So how many substituent? 2 carbon, ethyl. And how many carbon in the parent chain with the carbonyl group? 1, only 1. So 1 is methane, right? So methanoate, ethyl methanoate. So this is how you normally name any ester compound, right? So now let's try to draw the structure of an ester if the name is given. Let's do the opposite way, right? So till now we just learned about if the structure is given, how you're gonna name it, but right now we're gonna know if the name is given, how you're not going to draw the structure of an ester. So we're gonna do 3 examples. One is ethyl ethanoate. Then we have the second one, methyl propanoate. Then we have the third one, ethyl benzoate, right? So let's try to draw the structure for all 3 ester. The time I see the ending word is OATE, I know this is an ester, and then ethanoate means the parent chain has 2 carbon, right? So I can say 1 2 O O. So 1 2, this is your parent chain with a carbonyl group, right? Then this is an ester, so we have to write 1 more oxygen, and then this is your substituent. And if you remember, substituent will be those carbon that attach directly with a single oxygen. So how many ethyl is? Again 2. 1 2. So this is your substituent, this is your parent chain. So this is the structure for ethyl ethanoate. Let's do the second one, methyl propanoate. Again OH, ester, propane means 3 carbon. 1 2 3. So we can do double bond O O, and then methyl means just 1 carbon. So this is 1 carbon, methyl 1 2 3 propane OH, right? So this is the structure, right? So this is your substituent methyl, this is your parent chain. Let's do that last one, ethyl benzoate. The time I see OH, I know this is an ester. Benz means benzene, benzoate. So the parent chain has a benzene in it. 1. So let's make a benzene. And then benzoate means you have C double bond O, and you have a benzene R group. Then we have O, and then on single oxygen you have ethyl group attached as a substituent, right? So 1 2 1 2 ethyl group. So that's the structure of ethyl benzoate, right? So make sure you practice this kind of problem again from a textbook, how you're going to draw the structure of an ester if the name is given, or if the structure is given, how you're going to name it. So make sure you practice a couple of more examples, right, based on the concept whatever we just discussed on this video. Let's talk about our final functional group from this chapter, which is an amide. So amide is normally formed when a carboxylic acid react with amine, or you can say ammonia. Ammonia is NH3, right? So amide is also a derivative of a carboxylic acid. So in this case, if you see one of the amide over here, which is R CO and N, if you have something like this structure, carbonyl group attached with the nitrogen, this is an amide, right? And nitrogen has to make a 3 bond. One of the bond is already with the carbonyl group, right? Then we have other 2 bond on the hydrogen side, right over here, but this hydrogen can be replaced by an R group. So depending on which kind of bond the nitrogen attached, whether it's hydrogen and R group, we have a different kind of amide, right, too. So we normally write amide as NHR, NH2 or NR2. If you have NH2 means both the bond attached with the hydrogen. If this is NHR means one of the bond is R, another one is H, NHR. If both of the hydrogen get replaced with the hydrogen with the R group, then Nr2, Nr2, right? Nr2. Right? So remember this thing, how you normally differentiate. So like I said, this amide is a carboxylic acid derivative. Let's see why. So what is carboxylic acid? COH, right? If you remove, this is a carboxylic acid, if you remove this OH and replace with N, so this is your amide, right? That's why we call it, this is a derivative of a carboxylic acid, right? So let's see a couple of structure of the amide on the next slide. Example of the amide structure, you have HCON. This is your amide, but this is a simple amide. You don't have any R group in there, right? You have just single carbon. So we call as methanamide or formanamide. We're gonna learn about how to name this amide later on, but this is a common amide, thus the simplest amide you can say. Then again you have C double bond ON amide, and you have hydrogen on the nitrogen. So if you have to draw the line angle formula, the skeletal line, you normally show C double bond O carbonyl, and then on that carbonyl group you have NH2 in this case. In this case again carbonyl group has NH2, right? But in the third one you have 1 2 1 2, third 3, and then on the third you have a nitrogen attached with the hydrogen, and then you have 2 more carbon, 1 2, right? So this is how you normally identify which kind of amide you have, right? If there is a amide present in the functional group. So if you see over here in amide you have C double bond O N, right? This is a carbonyl, this is a nitrogen, and then you have a bond between them, carbon nitrogen bond, and this bond over here has some double bond character because of the resonance, right? So for example, if you have something like this, R C double bond O N H H, so if the lone pair goes over here, this double bond go on the top, and now you have 6 lone pair, right? So the structure will be like this, R C O double bond NH, right? Then after some time this lone pair will go again on this nitrogen, and this lone pair from oxygen make a double bond. The structure will make this type of structure one more time. So because of the resonance, the CN bond has some kind of double bond character in between them, right? And because of the resonance, it doesn't act as a base. Nitrogen doesn't have this electron as a free because it's a part of the resonance, so it cannot act as a base too because it's already being using in a resonance, right? So this is a common thing that you need to just remember in for amide, right? And then we already talk about that this hydrogen on the amide can be R, both of the R group, one can be R, one can be S. So this is a other thing that you need to remember for amide too. So let's go to the another slide and try to see which kind of molecule is an amide or not an amide. If you already understood, how you going to figure it out whether the given organic compound is an amide. So let's do this one. Which of the following compound is not amide? So that let's see the first one. So you have CH3, C double bond, you have CO. So this CO can be something like this, and you have N, you have H, means one of the bond is hydrogen, other bond is attached with CH3. The time you see C double bond O, amide. What about the second one? CH3, CH2, NH2. Even though you have a nitrogen, you don't have a carbon that is attached with the nitrogen has a carbonyl group, right? So this is not an amide. What about the third one? You have CH3, CH2, CH2, CH2. The time again you see CO, means this is a carbonyl group, and then you have NH, H, carbonyl plus nitrogen, amide, So B is not an amide, this is just an amine. If you remember from the previous chapter, you have a single bond between carbon and nitrogen, right? And this carbon doesn't have a carbonyl, so this is a amine, not an amide. Now let's try to name a couple of amide using an IUPAC rule. Again, what you need to see over here, first you have to identify whether you have an amide. The time I see this thing, I know this is an amide. So how you gonna name it? So the first thing, the ending word for naming of an amide should end with amide. It's not you're putting something else, you're just putting the name amide, right? Then the other thing that you need to remember, which kind of group is attached on the nitrogen. You have two kind of groups, one is R group, another one is hydrogen. So if you have any group attached with the nitrogen, any R group, you have to specify that thing as a substituent first. So you have to write which kind of group is present. 1, 2 is ethane, so ethyl, and you have to specify where you have this ethyl group attached, because this ethyl group can be attached to any of the carbon of the parent chain too. So you have to write this ethyl attached to the nitrogen atom. N represent the nitrogen in amide. So N-ethyl, you don't have to specify about the hydrogen, only the R group. Then the other part is a parent chain. 1, 2, 3, 4, 5, 6. 6 is hexane, N-ethyl hexane amide, hexanamide, right? That's the only thing that you need to worry about. If you have any R group, specify with an N. If not, you don't have to specify anything. Let's do one example over here. If you have this structure, double bond O, N, H, H. What's the name? The time I see double bond O, N, I know this is an amide. So this is, you have to find the parent chain. This is a carbon. 1, 2, 3, 4, 5, 6. You have to give the preference to the amide that has a carbonyl group. Then we have 6. 6 is hexane. Just write hexane amide. That's it. You don't have to specify whether you have 2 hydrogen, 1 hydrogen, right? Because both of them is hydrogen in there. Let's do a couple of more on the amide. The time I see this structure, I know this is an amide, right? And the nitrogen has hydrogen and hydrogen. So this is an amide. I have to give the preference to the carbon that is an amide. So 1, 2, 3, 4. So 4 is butane, butanamide. Simple. Let's go about the B. So the time I see again C double bond O N amide, and on the nitrogen instead of hydrogen, what you have 2 R group. This is R, this is R. So we have to specify as a substituent. So N, this is your ethyl, this is your methyl. So we have to go alphabetically. So N ethyl, N methyl, because you are specifying then both ethyl and methyl present on the nitrogen. That's why the symbol is N. And we are going alphabetically. N ethyl and methyl. Then parent chain is how many? 1, 2, 3, 4. 4 is butane, butanamide. Same thing over here. The time I see this thing, amide, and on nitrogen in amide, one of them is hydrogen, so it's okay. But on the other bond on the hydrogen, this is what? A carbon. This is methyl. So we have to specify on the nitrogen we have an R group, which is N-methyl. Then how many in the parent chain? 1, 2, 3, 4. Again 4, butanamide. Right? And if you have this kind of condensed structure, the time I see C double bond O N, I know this is an amide, and on the nitrogen one of the bond is hydrogen, another bond is ethyl group. So I can say N ethyl. How many carbon on the parent chain? 1, 2, 3. 3 is propane, propanamide. And if you want to draw the structure, you can draw the structure like this. CH2, C double bond O N, HCH2CH3. So this is your amide, and on nitrogen you have CH3, so that's why it's N-ethyl propanamide. So this is how you normally write the name of the amide molecule if the structure is given. So now let's do a couple of examples where I am giving you the name, you have to draw the structure, right, for the amide molecule. So let's do the first one. The name is N, N dimethyl butanamide. Right, so the time, and the second one that we're gonna do is we're gonna do ethanamide, and the third one that we're gonna do is we're gonna do N-methyl pentamide. So let's try to do all these structure by the naming. So again, you have to go with the parent chain. The time you see butane amide, I know we have 4 carbon, 1 2 3 4. Then this is an amide, that means C double bond O N, and then we have to specify which kind of bond you have on the nitrogen. So the time you see N, that means both the bond on the hydrogen are not hydrogen. That's why we have to specify N in the name. So what we have, methyl group, right? So one of the bond is methyl, another one is methyl. So this is the right structure. You have 1 carbon, 1 carbon. So this is the structure for N and the dimethyl butanamide. Good. Let's do the second one, ethane amide. So ethane is 2, 1 2, amide is N. There is no N written in the front, that means nitrogen has contained hydrogen on both the bond. So ethanamide. Let's do the third one, N-methyl pentamide. Pentane is 5, 1 2 3 4 5, 5. You have a carbonyl group, then you should have a nitrogen to make it amide, 1 2 3 4 5. This is pentane, and you have N-methyl. So one of the bond out of the 2 bond that contain the hydrogen replaced by the methyl group. So this and this is a hydrogen. So this is your methyl. So N-methyl pentamide, and this is a bond, amide bond that we have, C double bond O N. So again, so make sure you know how to draw the structure of the amide and practice from the textbook too, right? So that you can get better while drawing the structure by looking at the name, right? So at last, we're gonna just overview what we did in this video. What are the functional group that we covered? So we covered different functional group that contain the carbonyl group. One of them is aldehyde. Second one we did is ketone, then carboxylic acid, ester, and amide, right? So make sure you know the difference between the functional group of all those kind of functional group that we done, and just practice like a lot of problem from the textbook based on different functional group, right? Aldehyde, ketone. Then I think that should be it from this chapter number 12. Then I'll see you in the next video. Bye.